Alright, molecular polarity and intermolecular forces. Today we're going to be looking at a polar versus non-polar molecule. We're going to define what they are, as well as figure out what the intermolecular forces are at play corresponding to each of these molecules and differentiating between the two. So let's start off with a polar molecule. So polar molecule is when one end is more positive. We'll abbreviate this as more positive. Okay, this symbol, so more positive. And the other end is more negative. So one end being more positive, so we'll abbreviate it this way. So this one over here is going to be the more positive end. And this end over here is going to be the more negative end. Because we have these partial charges in play, where one end is more positive and one end is slightly more negative, we deem this as an electrical pole. However, in a non-polar molecule, this electrical pole does not exist. In a non-polar molecule, it does not. It doesn't have the charges present. At the ends. Due to the reason that the electrons, so this obviously stands for the electrons are finely distributed. Now this is important to understand because this means that both ends for this non-polar molecule are being shared equally. Now it's not exactly that straightforward of it being exactly equal in magnitude, but it's negligible enough where one end is not more positive than the other. Now let's have a look at a certain guideline that you would have to memorize. So you're going to be going from 0 to 0.4. Anything within that range is going to be deemed as nonpolar. Again, this isn't 100% accurate because in the next few videos that I'm going to be teaching you, it has to do with net ionic character as well. And the percent ionic character isn't as clear cut with these ranges. It has to deal with percentages, but we'll deal with that when we get there. So we have 0.4 all the way to 1.7. This is going to be deemed within this range as polar, and anything greater than 1.7, so let's say greater than 1.7, okay, is going to be ionic. Again, anything greater than 1.7, so 1.8 versus a 3.2 versus a 3.4, these are all deemed as ionic. This is why this chart here isn't as clear cut, just because remember, something just can be more ionic than others. A 1.8 value range versus a 3.3 is a huge difference. So when we look at percent ionic character later on in the videos, you'll start to understand why this kind of falls apart when we want to be extremely specific on either ends of the spectrum. All right, let's continue with the polar molecules. When we look at these polar molecules, there's going to be something that you're familiar with or have heard about before, which is the H-Knopf principle. And if you have an H with an N or an H with an O or an H with an F, it's likely going to be polar. So if I give you an example of, let's say, H2O, you have an H and an O, which is represented right here, is obviously going to be polar. So you would think right away H2O is polar, and it is. Then let's have a look at maybe like ammonium, NH3. You have N, and then H, and then H. Pretty straightforward. And then let's say you have something like hydrogen fluoride or hydrofluoric acid, H and then F, H and then F. And then we can even look at something like methanol, CH3OH. Again, we have your O's, we have your H's, have your O's, have your H's. Okay. Let's have a look at H2O. We all know what that is. So we'll have our H's, All right, we'll have to look at the valence electrons. So for the hydrogens, you have one valence electron. And then you have your oxygens, which has 1, 2, 3, 4, 5, 6. If you were to connect these together, you notice how the oxygen here has two lone pairs. There is one lone pair here and another lone pair here. When you have these lone pairs, you know right away that this is going to be a polar molecule. We are not even looking at this chart yet. We will, but just letting you know that one end of the checklist that I want you to know is, so is it nonpolar? Is it nonpolar? One in the bargain of the checklist, the first one, has to be no LP. LP stands for no lone pairs, okay? Are there no lone pairs? This is a question that I want you to ask yourself, okay? In this perspective, are there no lone pairs? So you look here, are there no lone pairs? Again, we're only looking at the central atom. Are there no lone pairs? I see one here. I see one here. So, to answer this question, are there no lone pairs? That's false. Because I do see the lone pairs. If I didn't see lone pairs here, and it asked it, no lone pairs, I would say yes. But because there are lone pairs there, I have to deem it as false. So I'm giving it an X. Okay? Now, it's not just about that. We also have to look at something called the electronegativity difference. So if I were to look at this chart over here, we're dealing with H2O, right? H2O. So we have to look for a hydrogen, which is over here, which is going to be 2.18. And we're also going to be looking at oxygen, which is over here, which is 3.44. We have to look at the electronegativity differences between the two. So we have, obviously, oxygen 3.44 and hydrogen is 2.18. The electronegativity difference is what we want. So it's just the difference between the two. So delta, right, which is the triangle, delta En, is going to be what we're looking for. So if we just do a quick calculation of 3.44 and 2.18, let's have a quick look at that. So that would be, I don't know, I think 1.26, right? So that would be 1.26. It's going to be the value of the difference between these two. And let's look at this value that we just looked at of 1.26. Where is it in the spectrum? Well, it's between this, and this deems that it is polar. So this is another tell that this is likely going to be polar. So the difference between here, okay, is 1.26, and the difference between here is also going to be 1.26. It's also important to establish that we put a direction vector going towards the oxygen, because this arrow here that is being pointed is going to be deeming it as the more electronegative side. So if this one has a stronger electronegativity value, which is going to be 3.44 over here, because it's a higher value, it's going to be facing, the arrows are going to be facing this element. And the hydrogens here on the sides are going to be a lesser value, so it's not as electronegative. So of course it's going to be more positive. The opposite of negative is going to be positive. So you're going to have these crosses on either side. Okay? Now you do see how they are canceling out. If they do cancel out, this can only happen if they're going in exact opposite directions, but also have the same magnitude. We've established that this is 1.26 and this is 1.26. So same magnitude. Are they going in opposite directions? Yes. One is going from here, right to left, and this one is going from left to right. So it meets those criteria. So they cancel out. The reason why I'm talking about that is because our second checklist here, we're going to be putting this in practice in the next video. But for now, I just want you to know that a checklist that I like to use is no hydrogens. Okay, no hydrogens. So if we look over here, do we see any hydrogens that are being attached to this central atom? There are. There's a hydrogen here and there's a hydrogen here. So when it says there's no hydrogens, that's obviously false. You have to put an X. However, there's a second little subset of this checklist. I want you to also put unless canceled. Okay? If they are canceled, you can revert this X into a check mark. Let's see. This cancel out with each other. So because they cancel, we can actually change this into a check mark. However, does this mean that we have deemed this as nonpolar? No, because this checklist is looking at both. It's looking at both checklists, and they must both be written off as a check. If they're both checked off, then this can be deemed as nonpolar. However, no. This is not nonpolar because we have that X over here. Both of these need to be checked off. So if they were going to ask you a question of is it nonpolar, the answer for that would be no, because there is an X. Only if there are two check marks here, then you could say yes, it is nonpolar. However, in our case, it's not the case. All right, so that is the H2O. If we look at something like, you have a carbon in the middle, and then you have your sulfur on one end, and then you have your oxygen on the other end. You should already know by now that the carbons, again, have 4 valence electrons, so let's combine them. Okay, with the elements on the side, so obviously we have oxygen here, so if there's 2 electrons that are making those double bonds, then you obviously need to have 4 more here to make 6, because again, oxygen has 6 valence electrons, and then same thing with sulfur, so we have these electrons that are bonding. So now I have 6 valence electrons for the sulfur. Now when we look at this, is this going to be a canceling out effect? It's not. It's not going to cancel out because we can easily tell right now that the electronegativity differences are different. This is why I'm talking about the magnitude. The magnitude must be the same, and if they're going in the opposite directions, then they can cancel out. In our case, it's not doing that. Let's have the carbon, the oxygen, and the sulfur in writing. Carbon, sulfur, oxygen. Our carbon here is 2.55. So 2.55. Let's have a look at our oxygen, 3.44. And let's look at our sulfur. It is 2.58. If you were to get the electronegativity differences of all of them, let's just quickly do that. So the electronegativity difference between the carbon and the oxygen gives you 0.89. Okay, but the electronegativity difference, obviously between the sulfur over there and then the carbon, is just going to give you a 0.03. As you can see, they're quite different. So over here we have 0.89, and here as 0.03. That's the electronegativity differences between the two. All right, now let's have a look at the direction of the vectors. So the arrow for this oxygen, it's going to be pointing in that direction. And there's 2 bonds, so technically we need 2 of those arrows. So they're going in that direction because this is the most electronegative. All right. If we look at the sulfur and then the carbon, sulfur and the carbon, 2.58 versus 2.55. So this one is going to be more electronegative. Now, you see how they're going in opposite directions. This is good news if you wanted to cancel them out. The problem is, like we've already established, that they are of different magnitude. So because they are of different magnitude, we cannot cancel them out. So this, all of a sudden, right away is going to be is going to be polar. All right? So, even though there are no lone pairs associated with this carbon, because every single electron, this one, this one, this one, this one, of carbon is already bonded, so there's no lone pairs. However, they do not cancel out. Okay? So because they do not cancel out, there is going to be partial charges distributed. Okay? Where one end is more positive and the other end is more negative. So because of this disparity, we deem this as polar. Again, it's only nonpolar if both of these checklists are met. Look at the disparities here. We look at the electronegativity differences, and again, you can look at your periodic table. Look for the electronegativity of each of these elements, and you should be able to tell that the fluorine here is extremely electronegative. So it's obviously going to be pointing in that direction. For the carbons and then the hydrogens, it's going to be pointing towards the carbon, and the carbon. Now you can see that they are going to cancel out from here and here because they're the exact same electronegativity difference. If you were to get this carbon and the electronegativity of hydrogen and get these two together, they're obviously going to be exactly the same, and they're going in opposite directions, so they cancel out really well. However, this does not cancel out with this. First of all, they're different elements, the hydrogen and the fluorine, so the electronegativity difference values are going to be different, so the magnitude is different. So even if they were going opposite directions to each other, it wouldn't really cancel out anyways because of the difference in magnitude. But as you can see here, they are going in the same direction, so the net vector is going to be in that direction, so they aren't going to cancel out. They only cancel out when they are in opposite directions. They're going in the same direction, so that's not the case. So right away you can tell that this is going to be polar. All right, again, there are no lone pairs there. Okay, so it's one step closer to being nonpolar. However, they absolutely do not cancel out. So because they do not cancel out, this has to be polar. Okay, now let's have a look at the nonpolar examples. If we have a few nonpolars, all of the diatomic molecules, by the way, are going to be nonpolar. So you know, your Hofbrinkel. So let's have, you know, N2, O2, Cl2, F2, H2, and then we have, I don't always use Hofbrinkel. I use have no fear of ice cold beer. So have no fear of, where's I, of ice cold beer. Okay, there we go. Right, so all of these are diatomic molecules. Okay, so all of these are the same. Now even the noble gases, so let's say the Ne, the He, the Ar, and the Xe, these are noble gases. And these are the diatomics. Okay, both of these categories here are going to be nonpolars. All right, so when we look at the diatomics, because these are these two elements that are exactly the same, of course there's not going to be one that's going to be greater than the other because the charges are shared equally between these two because they are the same electronegativity. So of course there's going to be not a lot of a fight of a tug of war going on. If we look at CH4, our methane, or carbon tetrahydride, quite easy to tell that this is obviously very, very symmetrical. Okay, we have the electronegativity difference going towards carbon. So all of them cancel out and they're all of the same magnitude. So this is obviously 100% nonpolar, and you can tell that there are no lone pairs over there. Okay, that carbon has no lone pair. So back to that little chart that we did, right? Is it nonpolar? Is it nonpolar? Okay, no lone pair. So that's obviously true. Okay, there's no lone pair. How about no hydrogens? Okay, that's obviously false. However, do they cancel out? Cancel out. They obviously do cancel out, so that changes into a check mark. So we have both check marks, so we can deem this as a nonpolar molecule. Let's have a look at C2H6. Of course, all of these have a electronegativity. So the carbons, it's going to go in that direction, that direction, that direction. This is obviously going to be spaced out equally. This one here going towards it, going towards it, going towards it. So of course these will cancel out, these will cancel out, and this one will cancel out. So this one is going to be nonpolar because again there's no lone pairs. Again, which one is going to be the central atom? Technically both. Okay, this here are both technically the central atoms. Okay, when we get to the hybridization, then we'll have to look at each of these separately, independently as the central atoms, but for now just know that both of these are central atoms. Again, there's no lone pairs on each of them because they're fully filled, right? This has an octet rule, right? 1, 2, 3, 4, 5, 6, 7, 8. Okay, for this carbon over here. And then we can do the same thing for the other carbon, right? 1, 2, 3, 4, 5, 6, 7, 8. So that's very, very happy with an octet. So there's obviously no lone pairs that are just flying around the carbon. And then are there no hydrogens? That's obviously not true. There are hydrogens, but they obviously cancel out. So this would be a nonpolar molecule. If I were to have a look at, let's say, CO2, we have carbon, and then you have your oxygens. Now the oxygens here are going to be double bonded, and if there are two bonds, as you can see over here, these two bonds are going to make this oxygen have two lone pairs, because that way it can have 6 valence electrons. Oxygen has 6 valence electrons, so this is the only way that this is going to work out. Same thing for this oxygen. There's 2 electrons over here, so then we need a remainder of 4 for this to work out. Carbon, so I'm just going to bring this a little bit closer. Okay, this carbon over here already has 1, 2, 3, so 4, so we're just not going to really touch that one. So we can see that there's no lone pairs here. If there's no lone pairs, that's the first checklist. Okay, no hydrogens, there's no hydrogens at all. So this is going to be nonpolar. So this is going to be for sure nonpolar. Our CO2 is going to be nonpolar. Let's just do one more. SO2. So our sulfur dioxide. So if we look at our sulfur, sulfur is going to be in the middle, and then we have our oxygen on the side. Sorry, I forgot to preface it. The reason why I am able to determine which one's going to be in the middle and which one's going to be on the outskirts, okay, you can't just do it based on face value of what you think. You have to understand that the lowest electronegative is going to be in the middle. The only exception to that would be hydrogen. As you can see, hydrogen has a very low electronegativity, I mean, compared to these guys, obviously, right? Especially more towards the far right side of the end. However, hydrogen is not going to be the central atom. Now, most of the time, like I said, the central atom is going to be the least electronegative one. So sulfur, less electronegative than the oxygens, in case you were confused throughout the video. So sulfur, we have it in the middle. We have 1, 2, 3, 4, 5, 6. Okay. However, we are going to establish here that the sulfur, rather than having these bonds, it's going to be bonded not by themselves, but it's going to be with the oxygens, as so. Sulfur has 6 valence electrons, so let's count them up. We've got 1, 2, 3, 4, 5, 6. Oxygen, again, it is now on the outskirts. It's not the central atom. Well, look at the bonds. There are 2 bonds over here. There's going to be 2 electrons. So how many electrons would there have to be left? There have to be 4 more left because, again, oxygen has 6 valent electrons. So I got 1, 2, 3, 4, 5, 6. We're going to do the same thing for this end. 1, 2, 3, 4, 5, 6. So this is going to be sulfur dioxide. Let's have a look. Are there no lone pairs? Okay. What do you see? Are there no lone pairs? That's a false. I see lone pair. This is going to be untrue. Are there no hydrogens? That's true. However, look, both criteria are not met. So because both criteria are not met, this X over here is going to deem this as this nonpolar cannot be answered. Okay, because remember, this nonpolar here, the real question, I just did this in short, but the long question is this nonpolar? Okay, is this nonpolar? The only way that we can deem this as yes to this question is if both of these check marks are in place. We don't have that here because there is one x. So to answer this question, is this nonpolar? I would say no. It is not nonpolar. Therefore, it must be polar. So SO2 is going to be polar. In the next video, we're going to be having a look at drawing out these Lewis structural diagrams and making sure that these intermolecular forces are where they are supposed to be, and that we can practice on our own with some review questions to determine if it's polar or nonpolar by the end of the Lewis structural drawing.